I'm pretty sure that most of us are familiar with the concept of faster than light travel, something that is forbidden in Einstein's theory of special relativity. According to Einstein and experimental evidence, nothing can travel faster than the speed of light. But what if there was some kind of loophole, a way to circumvent this limit and achieve speeds faster than light? Well, it turns out that there just might be such a thing. Special relativity states that nothing can travel through space faster than the speed of light, but in general relativity, which is the most complete and general theory of space and time, there is an exception. Space itself can stretch, move, and curve, with no limits on how fast these changes can take place. Enter the Alcubierre warp drive. In year 1994, a Mexican physicist called Miguel Alcubierre published a paper in which he found solutions to Einstein's field equations that allowed for faster than light travel. Since there is no limit to how fast space can bend, warp, stretch, and expand, these solutions describe a metric in which you compress the space in front of the spaceship, expanding it behind the spaceship, effectively creating a bubble of space-time that then moves through space. The spaceship itself then sits in a flat region of space between the expanding and contracting spacetimes. But the ship itself is not moving in space, it is the space itself that is changing shape, and that is what we call a warp drive. But then how would you go on to create such a warp drive? Well, you need energy, lots of energy, but not just any kind of energy. In fact, according to Alcubierre's solutions, you need a form of exotic energy with a so-called negative energy density. Or, since energy and mass are equivalent in Einstein's theory of special relativity, you need negative mass. Since energy and mass are equivalent, I will be using these terms interchangeably in this podcast. But as far as we know, negative mass does not exist. Not only would we need a kind of exotic matter that doesn't exist, but we would need 10 times more negative mass than there is of ordinary mass in our entire observable universe, effectively rendering it impossible to build such a machine. However, further reworkings of the warp drive model by physicist José Nattario and Harold S. White has completely removed this limitation. They found out that by manipulating the shape of this warp bubble, you can reduce the amount of negative mass needed down to arbitrary low levels. This means that we may only need a minuscule amount of negative mass in order to make an actually functioning warp drive a reality. But what is this negative energy or negative mass? Well, it's not the same as antimatter, because antimatter is just like normal matter, just with the opposite electrical charge, but it should have ordinary mass, at least as far as our theories go. Negative mass is an exotic kind of matter that reacts repulsively to gravitation and moves opposite to any forces applied to it. For example, if you were to push a block of normal matter, it would move away from you. But should you push negative matter, it would move in the opposite direction of where you were pushing. So it would move towards you when you push it and away from you if you were tempted to pull on it. But there is no such thing as negative energy. Or is there? Well, the universe has given us many hints that there might exist negative energy. One of the greatest examples we have of this is our very own expanding universe. We have an unexplained phenomenon in the universe called dark energy, which is the name we have given for the phenomenon of the ever-accelerating expansion of the universe. It is as if, at very large scales, all matter is being pushed away from each other faster and faster. Since positive energy results in a gravitational attraction, then negative energy would result in a gravitational repulsion, which is exactly what we observe in dark energy at very large scales. But we haven't got the faintest idea of what it is that is causing this accelerating expansion. Maybe it has something to do with negative mass. Only time will tell. But besides dark energy, what are other examples we know of that hint towards the existence of negative mass? We have a very real, confirmed, and often cited example of negative energy density, which has been observed in quantum field theory experiments. It's a phenomenon called the Casimir effect. The Casimir effect goes like this. Imagine you have two very thin metal plates in front of each other being very close together in a vacuum with a very tiny empty space in between them. Well, according to quantum field theory, empty space is not actually empty, but it is brimming with particles constantly popping in and out of existence. And the types of particles that can be spontaneously created depends on how much free space there is for them to appear in. Since in this experiment, the space within the two metal plates is very tiny, and the space on the outside is very large, then it allows for more energetic particles to be created on the outside of the plates than on the inside of the plates. This results in that we get a negative vacuum pressure within the plates, effectively pushing them together. This is the so-called Casimir effect. And since we have negative pressure being created out of absolute nothingness, we can consider this a kind of negative energy. Let me tell you of yet another more recent example of what might have been actual negative energy created in a laboratory setting. In the year of 2017, a team of physicists from Washington State University, by making a Bose-Einstein condensate out of rubidium atoms with fluid-like properties, and then manipulating them with lasers, they observed that some of the fluid behaved exactly as if it had negative mass, moving in the opposite direction of whatever force were applied to them. So we know it is possible to create phenomena similar to negative energy or negative mass, but we have no idea how to harness it, or whether if that is even possible. But what do our theories say? Well, there is no theoretical reason to discard the idea of negative energy or negative mass, except from the fact that it may violate causality, violate energy conditions, and so on. But besides that, even the current formulation of quantum field theory allows for negative mass in the form of virtual particles. Virtual particles are particles that form spontaneously in the quantum vacuum and exist only for a very short amount of time. In fact, they can only exist to the extent that the Heisenberg's uncertainty principle allows for it. But as long as they obey the uncertainty principle, there is no limit to what types of energies the particles may have. Remember earlier when I said that antimatter should have ordinary mass? Well, this is actually only something we believe in because until now there has been a perfect symmetry between matter and antimatter. But we have no direct experimental confirmation where the antimatter reacts gravitationally the same as normal matter. It may act repulsively, which could be interpreted as antimatter having negative mass. There was done experiments to measure the gravitational attraction of antimatter to normal matter in the alpha experiment at CERN, but the results were inconclusive. Based on all of this information, we cannot discard the possibility that negative mass may in fact be a very real thing, but further research is still needed. But if we can't discard the possibility of the existence of negative mass, we cannot discard the possibility of one day achieving warp drives and traveling faster than light.